Alright, time for another DraftPhysics.com video presentation. So a physicist, Michael, has made another video talking fundamental and elemental physics. Now, I'd say I don't know who this video is constructed for because the content is a mixture of first grade content and 12th grade content. There's no person this could be applicable to. So, that's my commentary to start with. He's basically just talking about how when you're doing math, math are just formalizations. They're just simplifications of the physical dynamics that take place in the three dimensions. And the three dimensions have dimensions, which are time is there. Okay, it's not a dimension, but it's a factor. Okay, then you have the distances, and then you have the velocity that you're traveling the distances, and then you have a mass, which is the amount of stuff that's traveling the distance in a unit of time. So there really aren't too many things you have to keep track of. There's just time, movement, and weight. And you'd never square a pound. You'd never say 6 square pounds. And it'd be just as illogical to say 2 square seconds or something like that, or 1 square second. It makes no sense. Okay, so I'm just going to talk about those points in his conversation where he starts talking as if these formulas have been proven somewhere, okay, that they're more than contrivances, where I would argue they double up on the squares or do some other kind of trick. Okay, like they did to Bernoulli. Bernoulli made a simple point that when you constrict the flow of a fluid under pressure, that the fact is you lose the amount, the mass, to increase the velocity, or vice versa. So it's a simple relationship, just like momentum, just like electricity, okay, where you have voltage and amperage. Amperage could be thought of as mass. Voltage could be thought of as speed. These are the simple relationships that are consistent throughout all areas of physics, and they have completely wiped all of those obvious connections out to play this squared game, okay, that really doesn't serve any purpose but to complicate things that are really simple. So the real mechanics is just mass and velocity. That's all there is in the universe that does anything. You see something happen, you just say, what are the masses and what are their velocities? That's all there is. And these extra little things they tie to that are all just nonsense. Putting halves in front of the math, or, the mass, and squares on the velocity. It's all nonsense. It's a square pound. It makes no sense. It has no purpose to square a time. Okay, said that, and so we'll go up to somewhere around here, and I'll
metric
check.
System, all other quantities.
Okay, so this is just simple stuff, okay? Obviously, just like Pythagorean kind of thing, right? I mean, you have to use the same units. I can't measure a triangle, let's say, and measure the bottom in inches and measure the side in centimeters, and then do the square times the square times the square to get the hypotenuse. I can't do that, all right? I can't find the right answer that way because 17 centimeters is not 17 inches. So I can't do the math without having the same units. And so this is just kind of obvious. And for time, it's obvious that we have 1 unit, seconds. We don't need any other thing. Everything else is a derivative of the second. Now with length, we have a real problem because we have feet and then meters and base 10 units and then base some other 12 units. I mean, it's not a very good. Weight is the same problem. Lots of ways to measure temperature. There's all kinds of ways to measure it, so it's all kind of nonsense. But again, you don't need any of the others but weight, speed, that's time, and what else? Weight and speed. That's about all you need. Mass and velocity. It's all there really is. All right, so we'll play a little tiny bit of this.
These are based on. Okay? So, for example, for time, I'm going to use these square brackets to denote the dimension of the quantity. So,
right, so there's no dimension of the quantity, okay? It's just It always has to be broken down into some sort of standard unit, and you just do multiples of it. You can do hours or months or years, and you just know that all of those things are derivatives of a second. And so you can have a meter, and then you can have a kilometer, and you can use different terminology, and you can know exactly that it means it's 1,000 of those units. It's not really that complicated. You have to have one standard unit that all the math uses, or the simplification, the formalization, the formula can't work, because it's simplification. It can't deal with complications. It has to be made simple. That's what makes math work, is simplicity. All right, so we'll pause here and I'll get to the parts that I find bad. I declare are bad science. All right, this part's a little bit funny. So there are new scientific units, SI units, are based on, these bizarre entities. So they're changing the standard from, let's just put something in a closet. So we'll put a second in a closet. We'll put something that weighs a kilogram in a closet. We'll put a meter stick in a closet. And we'll say, everybody use those measurements. Instead of that, they're going to create some sort of bizarre, and I call this rather bizarre, thing to measure that has to be measured with some sort of instrumentality that obviously all of the tools you're using to measure it are also have to be in some sort of condition to do they have to be a ruler that's precise to do the precision measurements to get your measurements. So it's kind of silly to say I have to have a clock that can count 1/trillionth of a second to be able to measure how long a meter is. I mean, it's that silly, really.
1 second is defined by a particular transition in cesium atoms, and saying how long does it take to go through exactly 9,192,631,770 transitions of this particular atom going through this particular transition. So people can go and measure that themselves.
Yes, yeah, they can. Sure they can. I'm sure it's really easy to measure that. Oh, it's just hilarious to count the cesium transitions in 1 second. No problem. Anyway, look, I'd say it's all good if they just establish a Planck number. Just say that everything's going to be made out of this idea that we know there's 1,000,000 of something in something, or 1,000,000,000. That's okay with me, all right? But still recognize that for practical use, you still have to put in the closet 1,000,000,000 atoms of, whatever, lithium. So you have 1,000,000,000 atoms of lithium in a straight line, and that equals a meter. Whatever that standard's going to be. But you still have to do it. So, but yeah, I think energy comes in clumps, okay, in quanta. And so everything should be quantized to the smallest unit of that thing. There is a smallest unit of distance, in my opinion. It would be, I guess, the width of a photon, and the element of a photon, excuse me, and some tiny entity. So those are real things that do exist, and photons have real momentum, blah 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 blah. So you can calculate that yes, a photon does move a certain distance at a certain speed, and the fact is it's always the same speed, so its momentum is pretty easily to calculate.
And say, okay, this is how we have now defined what a second is.
Okay, so that's all pretty rubbish. So anyway, moving on to the next bit. So you can't really read this, but it basically says speed is length times time, no square. So your speed isn't a squared function, but somehow your acceleration is. Even though your acceleration is exactly what your speed is. You're either adding to it or subtracting from it, and you're doing it in real units of 9.8, for example, per 1 second. Not per seconds. 1 second. That's the fact. The fact they ignore, the fact they distort and pervert without any good evidence or reasoning for doing it. Acceleration showed up very quick.
See how acceleration is a length divided by a time squared.
Why? There's no reason to square the time. Absolutely none. Acceleration comes in chunks, comes in units of it. Okay, you get a certain amount of it per unit of time. It's a clump of acceleration. It's not acceleration, open-ended, square something function thing. There's no squaring of a time. It's like this says length times 6 pounds squared. It doesn't make any sense. It's nonsense. It's garbage, rubbish, silly, not smart.
The generally assumed metric version of this is going to be meters per second squared. Yeah.
And again, no reason for the seconds to be squared. Your acceleration is just going to be a number of units of acceleration in terms of a change in a velocity. So you'll go from 60 miles an hour to 50 miles an hour, or 60 miles an hour to 70 miles an hour, and the change will be 10, miles per a single unit of time, an hour, 1 hour. In 1 hour, you change the speed by 10 miles per hour. That's it. There's nothing else to it. There's no squared function. You don't square anything. It's just 10. It's not 10 squared. It's just 10. It's just 10.
We're going to actually find evidence backing this up in the...
So there's no evidence backing it up. I've made the counter argument that gravity is clearly 9.8 meters per second. You're only in the gravity twice as long when you fall 4 times the distance. You're only in the gravity twice as long. You've only increased your velocity by 2. You've only increased your weight by 2. So again, this squared function is just nonsense. There is nothing that has been squared. You haven't done the square amount of work. You don't have square amount of energy. All you have is twice the momentum. All you're doing is increasing the velocity by 2.
The next video, a testing physics video. Force.
It'll be crap. All right, so again, he's got the squared unit on force. It doesn't belong there. There's no reason for it. There's absolutely nothing about force that's squared. Force is momentum. Newton said it clearly. Okay, it's just speed in most cases if you're not changing the mass. Clearly, Newton explicitly said you want to go twice as fast, you apply twice the force. You want to go 3 times as fast, you apply 3 times the force. Force is just a change in your velocity as an effect. That's all it can do, is change your velocity. That's all forces do in the universe, is hit something and change your velocity.
Well, that's going to be a mass times a length divided by a time squared. And for force specifically, we actually come up with a new definition, what we call a Newton of force.
Right, and that's just weight. So Newtons are just weights. So that's it. It's just a pressure. All right, and the pressure is applied over a specific amount of time, but there's no squared function. Again, no reason to square any seconds. Nothing needs to be squared. It's just a kilogram meter second. There is no seconds per second. There's no seconds squared. It's nonsense.
And 1 Newton of force is defined as 1 kilogram times a meter divided by a second squared.
So 1 second squared, which would be 1. So again, it's just deceptive. These formulas are all basically, you're saying it's a meter per a second. It's 1 meter per 1 second. That's the truth. Until you add more mass, or you add more time.
So again, these new units, for example, newtons, we can define those in terms of our base SI quantities. Similarly, when we talk...
This would be the replacement for what was called the foot-pound. So this is what you get when you just multiply mass times velocity. Not squared velocity, just velocity. So mass times velocity gives you newtons.
Talk about joules of energy, or watts of power, or Tesla.
So again, and watts are very so consistent. All right, that's the one that's just so obvious. It's just the velocity, the voltage times the amperage. No squared units. No need for square units. Nothing has to be squared to get a watt. And likewise, in all these other circumstances, there's no reason to square any portion of a velocity or the change in a velocity. There's no squared amps.
Of magnetic field strength. We can
There's no squared voltage, I guess is the real point.
Describe those in terms of these base SI units and these...
So the word is derive, which means they can just mathematically take formulas that are rational and they can combine them and create Frankenstein formulas that, yes, occasionally get right answers, but don't do so consistently.
Different dimensions that we've defined here, these kind of base dimensions.
All right, so I'll see if there's something. I know there's some more stuff later to point out. I think he goes back to first grade here for a while. So again, this is sort of the trivial part. So he's talking about his technique for converting miles into kilometers. And it's like he puts this fraction in here so you can cross things out. But why don't you just do the multiplication? If you already know 1 mile is 1.61 kilometers, and all you have to do is multiply the 8 times 1.6 and then do the rest of your equation. So what's so complicated? It's not complicated. So I don't know. You know, I don't see how that saves you trouble at all.
Again, this is a fairly introductory version.
Oh, yeah, exactly. And then you're going to talk about integrals and other stuff, and you're going to talk about squaring time, which you're not going to explain at all, why it makes any sense at all to ever square a time, why you would even say something like per second when, well, of course, everything is per second. Everything can be more than 1 mile an hour or more than 1 hour or less than 1 hour. Anything can be multiple units of something. Yeah, I can have 5 seconds worth or I could have 2 seconds worth. But it's got to be in units of seconds. As you're pointing out, the units have to be consistent. Why would I square a second? What does that even mean? How can that mean anything? Square pound. What could that possibly mean? 5 square pounds. What could that mean? Can't mean anything. It has no physicality. There's nothing in the physical world that represents. Your math should represent things as that are real, not abstractions. Even if you can use the abstraction to create a formula that sometimes works, it's not worth the price you're paying because it's incoherent. It's nonsense. And because you fix the nonsense with a counter argument, like the Bernoulli argument, they force it to be a kinetic energy formula. So they start squaring, numbers, and then they create a fake alternative abstraction that has to go with the formula that undoes the squaring because it squares a negative quantity, a quantity that changes directly proportional to the quantity they're squaring. So they create a fake entity that goes down the same amount as their fake kinetic energy went up. And it's all contrived. It's all breaking something really simple. Mass and velocity, really simple. Voltage and amperage, really simple. And they're breaking it, to create nonsense math. All right, well, here's a little bit that just seems really sloppy. So he's talking about volume, how it's length, width, and height. And then he basically creates a formula that says length times length times length equals length cubed. Well, it's not length cubed. That would have to be because that would have to be a perfect square. So he doesn't talk about volume of a cube or a perfect sphere. He's talking about volume in general, and you wouldn't just generally say, I'll just take any length and cube it. That doesn't make any sense. So this doesn't make any sense. I mean, you're not multiplying the same L, so I would just say the answer is L cubed. It's not. It's not any one of these L's cubed. So that's a little, too silly almost. So play a little.
Those correct units of volume. If I look at something trickier, like angular momentum, the angular momentum of a point particle around some given axis, so if we choose an axis and we have some particle move...
Okay, and this is just all nonsense, So angular momentum is, as the word says, momentum. It's not angular kinetic energy. And he's going to do the same thing here. He's going to square a function here, and there's no reason to square it. There's absolutely no reason to square anything here because it's a real distance it's traveling. It's a real momentum. It's angular momentum. So all you're really saying is yeah, it's going to be moving a real velocity, okay, around the curve. All right, and it's a real velocity. And the fact is that the r, the distance, is exactly the same as for a linear equation, for linear momentum. It's twice the distance. It's going to be twice the travel time, twice the travel distance. It's going to be exactly the same. It's going to be quite linear. So there's absolutely no reason to square anything because it's not going to be more momentum. So if I have two equal wheels, solid wheels, and I put a mass, a half mass out here, and I put a full mass here, twice half the distance, those wheels now have exactly the same energy potential. It'll take the same exact energy to move them, to spin them, and they will collect and hold the same exact amount of energy because the matter I've added is going a momentum, a real momentum. And it's just momentum. There's no kinetic factor. There's no squared factor. The half mass twice the distance is exactly the same energy in its movement. It holds the same exact energy, the same exact momentum. So you've added the same amount of weight essentially to the wheel, and there's no difference in terms of moving that weight. The amount of energy you'll need to move it or the amount of force it will apply when it hits something. It'll be exactly equal. And their mass says otherwise. It pretends to say otherwise.
In some way, it's going to be what is the distance from the point that we're measuring the angular momentum around to where that particle is, crossed with the momentum of that particle. And the momentum is mass.
Absolutely no reason to cross anything. Okay, just understand that the distance will just tell you in units. You have 1 unit of distance, you have 2 units, you multiply by 2, you have 3 units, you multiply by 3. Nothing gets squared.
Times velocity. So if I want to know what are the dimensions, what kind of a quantity is this angular momentum, well, that our distance, that's going to be a length, and our momentum is a mass times a velocity. We said velocity was a length divided by a time. So if I combine these together, that's going to be a mass times a length squared divided by a time. That would be the combination of dimensions.
So of course you don't square the length. You're squaring r. There's no reason to square it. There isn't a squared amount of momentum that's going to be created. It just means that the arc, the amount of travel you do per distance, per angular distance. So he's talking about angular momentum in the sense that he's saying velocity isn't real anymore. Okay, I'm going to talk about some sort of how much angle does something move. And they're not the same thing, obviously. So there's no reason to do it because momentum answers the question. So you just ask how much momentum does it have? The end. There's nothing, you don't need to complicate this with any of this rubbish. You just know that if you increase the mass, you decrease the distance. Period. The two are inversely related and the velocity will follow along.
That give us these dimensions for angular momentum. For other kinds of operations, let's say I'm taking a derivative. So this is going to be...
Okay, so this is the part that's funny, right? Because he's going to talk about derivatives and integrals in a video where he's talking to people about how they can't mix centimeters with inches. I mean, you know, whoops. Yeah, so now he's back on acceleration. So he's saying he's taking a derivative. The change in the velocity versus the change in time means somehow you're squaring the time. So that's what he's going to pervert it into. So let's see how he does the exact perversion. Because there's absolutely no reason to do it. None at all. It doesn't need this perversion.
Well, if it's that derivative, the dimensions are going to be the dimensions associated with velocity, so a length divided by a time.
So it's not. Velocity isn't a length divided by a time. It's an actual movement through space. And the only way you detect it is to do a length by time. But velocity itself isn't a length and a time. The velocity is a movement. Okay, it's a quantity, again, of energy, essentially. And the mass component adds to that energy. So the more mass you're moving that speed, okay. So if they just kept the word speed, then they wouldn't probably have a justification for any of this nonsense.
divided by the dimensions of the variable that you're taking the differentiation with respect to.
So again, this doesn't make any sense at all, because in most cases the acceleration happens in such a short period that you couldn't even figure out what time unit to put it in anyway. And it doesn't matter, because it's a unit of acceleration. It doesn't matter whether you change how fast something's going in 1 second or you change it in 5 seconds, especially if you're calculating over hours, something's real velocity. So it won't make any difference. And the fact is that the acceleration is just a unit of change. It's 1 unit of change. That's it. It's not a continuous change. It's just 1 unit of a change.
In this case, we're
like gravity. It's 1 unit of 9.8. It's not multiple units of 9.8. It's 1 unit in 1 second.
We're taking the derivative with respect to time. So we have to divide by another time. So overall, these dimensions for acceleration are going to be a length divided by a time.
So part of that doesn't even make any sense, because he's somehow crossed the t's out to create the L by itself and then doubled up on the t's or whatever. Doesn't sound logical to me. It doesn't look logical. There was no reason to do it anyway, because there's not really 2 times here that are the same time. This time is not the same as this time, and therefore you can't use time squared because they're not the same times. The amount of time you use to detect the velocity is not the same time that the velocity itself was accrued over. How you're detecting the velocity is not the same unit of time that you're using to detect the acceleration. There's no reason for those 2 times to be the same.
Squared. Again, generally, we're going to be using metric units, so it's going to be a meter per second, a meter per second.
Right, so it makes no sense. A meter per second. It's gobbledygook, garbage talk. Nobody should have any reason to ever say it as a physical event going by. You don't say the bird flew by at 20 miles per hour. It's redundant. Yeah, it flew by at a certain speed. How many hours it flew, who knows? Why am I squaring it? Why would I say per hour and then say that means I should square how many hours it was flying? No, I shouldn't.
And squared for the units of our acceleration. If I'm taking an integral.
Alright, so we won't bother with that. Alright, so moving on. Alright, so this part's the part where he gets to work, and he's going to talk about integrals using the work equation. But clearly, the work equation is complete nonsense. Alright, so and I'll just use this as a simple example. They're saying their math, their formalization says I'm not doing any work, when I'm clearly forcing this thing to stay up here instead of going down there where gravity's pushing on. I'm fighting gravity. I'm obviously doing work. I'm applying a force. All right, and the force is being countered by gravity. I'm doing work. So that's how bad their math is, right? They say this is 0 work because all they care about is distance, how far something moves. And it isn't about how far something moves. It's about how much time did a force affect it. So in gravity, it's about how long you're in the gravity. If you're in the gravity 2 seconds, you get 2 units of force. You'll have 2 units of velocity, and you'll have 2 units of weight. So this is just absolute crap. The work equation is contrived crap invented in the 1840s or so. Just nonsense. It's convoluted math just created to justify 1/2 mv squared. It's not for any other purpose but to force their understanding of energy to be more consistent. That's it.
Integrated over changes in position.
So it's not about your change in position. It's about, frankly, your very real velocity, and whether or not your real velocity is a consequence of 2 opposing forces. In the example of me holding this battery, there are 2 opposing forces, and they're really active forces, and there's real energy doing work.
So I'm saying how much force is being applied, and I'm adding up, when I'm doing this integration, I'm adding up the force times all of these little changes in position, and then I'm adding up all of those particular effects to get that full total amount of work.
Right, and the total amount of work is a big fat lie. As I've pointed out, you can roll an object on a surface. It'll go 4 times further if you give it twice the velocity. It doesn't do 4 times the work. It doesn't vibrate the ground 4 times as much. And Galileo proved it 500 years ago. 500 years ago, Galileo explained it. Yeah, these are the same unit of time. This much distance is the same work as this little distance over here. So the last quarter of the trip will take from you the same amount of energy that the first 3 quarters took from you. That's the facts. He won't counter that argument with anything rational. He won't explain why Leibniz's interpretation is better than Galileo's interpretation, or Newton's. He'll just state that we have to believe this. He won't explain it or justify it. He'll just say, we say so.
Yeah. Well, our dimensions of force, we said that's a mass times a length divided by a time squared. We said a Newton was a...
And now he's going to times it times another length. I mean, now he's going to have a mass times a length squared. I mean, it just gets too silly. So forget it. All right, we'll see if there's anything else. All right, so here he's going to talk about the joule. So I just thought we'd throw it in there because he's saying that this quantity, this squared quantity, is defined by a joule. And I just think the big joke is that Joule never proved that. He never proved that there was 4 times the energy. None of that ever was part of what he actually did with his experiments. So that's one of the ironies, is they're calling the product of 1/2 mv squared, okay, a joule, but Joule's analysis basically doesn't prove that, unless you misinterpret what a falling object is and how much energy it has. So again, if you go by distance, if you think something weighs twice as much or 4 times as much when it hits the ground, then you could argue that 4 times the distance is 4 times the energy. But it doesn't hit the ground with 4 times the energy. It only hits the ground with twice the weight. So this is more of the bull. And the scales prove it. I mean, you drop something on a scale from 4 times, you drop it from 1 centimeter, then drop it from 4 centimeters, it's only going to weigh twice as much. I mean, this is the big fraud.
Time squared. The general definition of this, the general metric units, are going to be kilograms times meter squared over second squared, and we call that a joule. Again, this is another one of those.
So a joule is equal to a watt, and so this is where you can know where this stuff goes silly, is that if you think about every time they talk about a joule and you just think of it being a watt of energy, of electricity, you can understand how it doesn't make any sense that they say the gun recoil has 2 watts of energy and the bullet has 2,000. Not true. They have the same momentum, and yet they're going to argue that one can create more heat than the other. No, it can't. If you hooked them up to Joule's propeller, okay, in the water tank, one of them isn't going to raise the temperature more degrees centigrade. So that's the irony. If they actually tested this theory, they would find that a mass going twice as fast does not heat the water 4 times as much. It doesn't happen. And yet they preach this falsehood, and with this huge implication that Joule endorsed this logic when, you know, Joule definitely thought of mv squared as being correct, but it was mv squared, by the way. But, you know, that's only because every other physicist was believing it. You know.
Derived quantities. So again, we can perform these different kinds of operations and look at what...
Okay, so that's all kind of useless, I think. Oh, we're still recording now. Pause.
So
all right.
All of these quantities, all of these terms must have the same dimensions.
So here he's saying a constant acceleration, which is just calling x, okay, has to be based on this 1/2, F equals ma. when no, it's just F equals velocity, F equals mv. Okay, it's just your momentum in the end. And your momentum will tell you how far you're going, because your momentum is going to tell you how fast you're going if you don't change the mass. So there's absolutely no reason for this other term in here, because all you really need to know is how fast are you going. I mean, you can plot it. You could draw it on a chart. Okay? And you can find out how far you're going to go going 30 miles an hour. You could just draw it on a chart, and you can see how far you're going. Anyway.
Let's check this. Well, my final position, that's going to be a length, some kind of distance. Where am I? Okay, so that's going to be a length. So everything else also has to end up as a length. Well, my initial position, cool, that's also a length. Pretty straightforward.
So that doesn't even make any sense, right? Because your initial position is where you're zero. It's not an initial, it's not a quantity, because you're just saying how much has my initial position been changed. So you've either changed it in one direction or the other direction, but there's no need to think of it as a quantity that has any relevance.
This middle term, initial velocity times time. Well, velocity is a length divided by a time.
So again, they keep doing this. They keep saying velocity is how you detect velocity, how you discover velocity, and that it's not something in and of itself. It's a velocity. It's how a speed. It's not, okay, what you use to detect it. What you use to detect it is not what it is. Because you can detect it over 5 minutes, or you could detect it over 2 seconds or 2 milliseconds. You could change how you're detecting it. All right, so there's just no point in doing that. There's no point in this derivative. Changing velocity into a fraction. You don't need to do it.
And
It's a ratio. How many miles per how many seconds? That's all it is. It's a ratio.
Multiplying that by a time. So those times are going to cancel out, and I'm left with just length.
So times cancel out. So here it has 1 over a question mark. I don't even know what that is. And he called that L over T2, so he could cross out the square on this time. So what was the purpose of the square? Oh, that's right, didn't have a purpose.
This last term, the 1/2 acceleration times time squared. Well, acceleration is a length divided by a time squared, and we're multiplying that by a time squared. So the t squareds can't.
Right, so you could have done without them right from the beginning. You could have just forgot about writing this whole hunk here. You could have just said, forget it. Don't bother. It's not going to do anything useful. All right, I'll see if there's something else. All right, I think he's back on work again.
Oh, different types of energy. Well, we talked about work, how work is the integral of force over displacement. And so the dimensions of that work are a...
So the challenge would be that it's actually force in time, and that's it. So the argument is that no, the length doesn't matter, the time matters. So as if I'm going outside, I'm going to get a suntan, and I decide to, walk slowly across the yard, so I can walk 10 meters in a half an hour, let's say, slowly, just meander. Or I can go really fast and be done in 5 minutes, or I could be done in 3. Obviously, I'm going to get more sunburned the longer I'm in the forest, the longer the sun's hitting me. It's about how much time I spend being affected by the force. It doesn't matter how much distance I'm walking. So if something's flying by a gravitational body, all that matters is how fast is it flying. That will decide how much this it gets. How many units of energy in this direction will be decided by how long it spends traveling this distance. And that's what's going to decide. The distance doesn't decide. The time decides. Now, obviously, distance and time can be related. All right, and there can be constants even about distance and time to force a relationship. So, in some cases, it's not going to matter which one you're measuring. But obviously, in cases like this, it will matter. In cases like gravity, where an object is falling 4 times the distance and appears to be doing 4 times of something, it's actually doing 4 times of nothing in terms of collecting force. It's only collecting force for 2 units of time. It only has collected 2 units of force, and it only has 2 units of energy.
Mass times a length squared divided by a time squared. And you can think of work as the amount of energy that's either being added to a system, if it's positive, or the amount of energy that's being removed.
There's just no reason to have this word work. The word energy already answers all the questions, okay? So there's no need for something called work. Work is just a portion of something's energy, usually the portion we want, the portion we're interested in. So we talk about how much work something does in the sense of we want the portion that knocks the bowling pins down. We call that work. And then the portion where we vibrated the lane that we threw the ball on, we call that waste or loss. But they're both exactly the same thing. It's the same extraction of the ball's energy is taking place in both circumstances. It's doing work on the alley. It does work on the pins. It's just a transfer of energy. So this word is meaningless. It doesn't have any meaning. It just has to do with what do anthropomorphic humans wish to project on energy. And they say this is the good fun energy, the work. Okay, and the bad evil energy is the, whatever you want to call it, the heat. The stuff that went some other direction and did some other thing. The portion that we don't use we call something else, and the portion we use we call work. So it's just crap.
From a system, if it's negative. So if that's an energy, all other kinds of energy must have these.
So it's not a kind of energy. Work isn't a kind of energy. Every single time something interacts with something, it's doing work on it. There is no differentiation between this kind of action and that kind of action. They're all interactions and they all involve something working on something.
Same dimensions. Well, let's look at kinetic energy. The equation for kinetic energy is 1/2 mv squared.
Invented by a religious kook who thought Newton and Descartes were 2 atheists, and their physics was 2 atheists. So he invented the living force. And yeah, nobody believed it because people made the logical argument a year later when Newton published and explained everything in detail. And there was no need for any squared term in anything Newton detailed.
So we've got the dimensions are going to be 1/2 doesn't have any dimensions, so we don't worry about that one. Mass is just a mass. Velocity is a length divided by a time, but we're squaring that velocity.
For no good reason. We're squaring a pound. It's a squared pound because we've decided. I mean, if they put the square on the m, everybody would say, "What the hell are you talking about? You can't square a mass. How do you have a squared mass? It's just too silly."
So both the length is going to be squared and the time is going to be squared. So we get mass times length squared.
Again, why the length is squared, I don't even see where that's in here anywhere. I don't know where in mv squared it says something 1/2 mv squared. I don't know where that says anything about a length squared, but okay, whatever.
Divided by time squared, matching our dimensions for work. What about gravitational energy? If I'm on or near the Earth, the gravitational energy is the mass of the object. If I have some object that I'm moving around to different locations, the gravitational energy is the mass of the object times the gravitational acceleration at this location on the Earth, so 9.8 meters per second squared if you're...
No, 9.8 meters per 1 second. You get 1 unit of 9.8 for every 1 second you are in the force. That's accurate. What you're saying isn't accurate. It isn't the truth. It isn't real. It's not accurate. It's just junk. Made up junk.
At most locations on or near the Earth. And y is just how high up in the air is the object situated.
Right, and it just says how long will it have to fall. So the height just has a relationship to time, because height is just saying how long will it fall before it hits the ground. If there's no ground, there would be no height, correct? So you'd really have to know that you really have to just calculate the amount of time. Why would I have to have a ground in the way? Why couldn't I say from this position to this position? All right. I mean, it's, so again, it isn't about anything other than how much time you spend being influenced by the force will decide how much energy you collect from the force. It's just like photons. It's the amount of time you're exposed to the sun will decide how many atoms got ionized.
Well, the mass is just m. Little g has units of length, has dimensions of length divided by time squared, and we multiply that by another length. So when I multiply these two lengths together, I'm going to get mass times length squared divided by time squared. Again, matching our definition of work.
Matching a ridiculous definition, and again, that's why the two things are related. Again, the work equation was contrived to create that relationship. It was contrived to make the math circular. So one part could end up defending another part, and then that part could defend that part, and it could just keep doing this. The one judge could tell the other judge, you're innocent, and then that judge would say you're innocent to the other judge, and they would just confirm each other's innocence.
One more of these, the spring potential energy. Well, the equation for spring potential energy is 1/2 kx squared, where k is the spring constant.
So again, kx squared only if you're looking for the spring energy in kinetic energy. If you want to know what its momentum is what kind of momentum it'll produce, then you don't square any of the terms. And the momentum will be the real number, and the kinetic energy is the fake number. So, we've been there and done that. So I guess I'll pause here and see if there's something new. All right, so here towards the end, he's talking about a Galilean thing again. Okay, the whole point of Galileo rolling things down the ramp was to slow down the process of gravity. That is, was to make the object fall over a longer period of time so he could actually see it. And he actually put bells. He made very long ramps, put bells on the ramp so he could hear that the intervals were as he was predicting, the 1, 3, 5, 7, the odd numbers. So the amount of distance increases in this proportion. 1 unit of distance for 1 unit of force. 3 units of distance for the next 1 unit of force. 5 units of distance for the next 1 unit of force. So it's just ironic that they're using this non-Galilean math, non-Newtonian math, to solve a problem that Galileo solved, quite accurately. And obviously the difference in the time means you are actually in the gravity longer, you are being exposed to the force longer, but you're also putting a lot of energy into the ramp. So all the extra gravity you're being affected by isn't going into the object moving, it's going into vibrating the ramp, the friction with the ramp, the weight on the ramp. That's where all the extra gravitational energy goes. So you end up with exactly what you would have ended up with if you just dropped the object, but you end up with it over a much longer period of time. So, this is just, again, convoluted contrivance math.
Change this, and we get that the acceleration is 2 times the length of the ramp divided by the time it took to go down the ramp squared. Again, this is in the case where we are assuming that we're starting from position 0, and we are starting with the cart at rest. We're just releasing.
Right, and this all is again contrived to cancel out. So have one thing cancel out the other thing, so you get rid of all these squared terms because they're of no value. They're not going to give you the right answer because gravity doesn't come in squared quantities. It comes in single units.
The cart from rest. And if this is right, if this has the opportunity to be right, then the dimensions on either side of this equation still have to match up. Well, when we check this, acceleration, those units should be a length divided by a time squared. And when we look at this combination of terms, we get a length divided by a time squared. So this matches, and it has passed this particular test.
So whatever, it's not really a test of anything, but whether or not you can contrive something, whether you can unnecessarily complicate, whether you can put a unicorn horn on a horse. Yeah, you can, but why would you? You might fool some of the people some of the time, but yeah, whatever. All right, so we'll pause here, see if there's any. I don't think there's much else. All right, so now he's on gravity. Now, I've been over this one before. This formula really isn't right, okay, frankly. Okay, so in my opinion, because they're two distinctly different forces. So when two things are in gravitational effect with each other, there's not one force, the force of gravity. There's this one pulling on this one, so to speak, right? This object's getting pushed into this object. This object's getting pushed into this object. There's two completely different forces involved. Each one has their own gravitational field. And so it's not really sensible to say, let's combine those two and add up how close they're moving towards each other or something. That's not a very useful term, especially if one is moving away, and if they're moving away from each other. It's not, in my opinion, useful at all. So it's much smarter, or better, to just recognize that this one is creating a field and this one is creating a field. And obviously with different masses, this becomes kind of obvious that the lighter thing is going to get pushed into the heavy thing at a much rapider rate than the heavy thing is going to get pushed into the lighter thing. The force being applied to the heavy thing is going to be a tiny force versus the huge force the heavy thing would be creating on the light thing. And this formula sort of breaks that continuity. So I don't personally think it's a great idea. Yeah, I don't think it's a great idea.
Are away from each other. So the centers of these spherical masses are a distance r away from each other. That gravitational force.
I would just add the two forces. I would calculate the force that M1 creates separately from the force that M2 creates, and then add them, rather than multiplying them separately.
Should be equal to Newton's gravitational constant, this capital G value. It's just a constant value.
And it's a constant value based on the fact that we've already established what we call a meter in a second. So if we change what a meter is and a second is, then we would change the constant. But because we have the meters per second, then the constant works, because the constant's essentially in meters per second. And it's just there to point out that the strength of the force is in those units.
Times the product of the masses divided by the distance between those masses squared. So if I change the values of those masses, or if I move...
The squared is just the r squared being doubled again. So the fact is the force diminishes by the r squared rule, so the distance matters. How far away you are from something will decide how much gravitational effect you have on it by this squared function.
Those masses closer together, further apart, this allows us to calculate what is the strength of that force of gravity.
So it's not the force of gravity, it's two separate incidences of gravity. The gravity created by the one object on the other object, and the vice versa.
This value of G, this capital G, what dimensions does it have? What kind of dimensions or units does it have? Well, for the gravitational force,
it just has to have units of meters and seconds. So it just doesn't matter, because it's wouldn't be a number without the units first. You have to have the units first before you can say what the number would be. But it's just a constant to balance the fact that we don't have a 1 to put there. Okay, so that's probably enough. Alright, so we'll call it a video, and such, and so forth, and whatnot. And so we'll see. He's going to keep saying he's going to prove something, so we'll see what he proves. He said previously in a video that all of these experiments have been done, and we have tons and tons of evidence. And again, my plea is, if you're going to say something's true, then show it to be true. Show us some real evidence of it being true, some real experiment that produces these results, and preferably an experiment that is something really connected to the result. That is, if you claim it takes 4 times the fuel to go twice as fast, or 9 times the fuel to go 3 times as fast. Will you show me where that happens? Show me it happening somewhere on planet Earth. And such. And so forth and whatnot.